Okay, so now what we're going to do is we're going to look at polynomial functions and roots as one whole topic. So this is going to span 3.2 to 3.4 in the text. So I've made this a bulk section here, and I've split it then into two parts, part A and part B. So let's start here with part A. So polynomial functions. Now, we've actually been looking at polynomial functions quite recently. We were looking at quadratic functions, which are second degree polynomial functions. And before that, we were looking at linear functions, which are first degree polynomial functions. So let's generalize. All right, polynomial functions. A polynomial function of degree n is a function of this form. Okay, we've seen this before because when we looked at polynomial expressions and polynomial equations, it was the same idea. You know, we have our, starting with our nth degree term and going all the way down to our constant term with all of our a's, which are our coefficients. Okay, and that's these a's are the coefficients. So basically we have a sum of a bunch of powers of x, and those powers of x again have to be 0, 1, 2, 3, 4, so the whole number powers. Okay, so no fractional powers here, no negative powers. So here are some examples. So here's a fourth degree polynomial. Again, remember the degree is the highest power in the polynomial. So that's why this one is a fourth degree polynomial. And here's what type we were just looking at with quadratics. There's a second degree polynomial. All right, so what we want to do is we're going to want to make our way to sort of factoring these polynomials and finding roots of these polynomials, which was fairly easy when we had something like a quadratic polynomial, because we had a nice formula for that, the quadratic formula, and we could easily find roots, zeros of the polynomial. So we'll talk about what those words really mean later on. So how can we go about doing that maybe for something like a fourth degree? Given that, well, to tell you the truth, we could come up with a formula for the fourth degree, but it wouldn't be very pretty to work with. And the fact is that once we get to fifth and beyond, there actually is no formula, so we need a more general way. All right, so we're going to start out with talking about dividing polynomials. Okay, so that's something that we avoided when we were doing polynomials much earlier as expressions. We learned how to add them and subtract them and multiply them, but we didn't talk about dividing them because it's a little more intricate. So let's see. So consider a polynomial f of x, and you're going to divide it by a polynomial h of x. So what happens? Well, when you take it and divide it, as with the numbers, you're going to get a quotient, but this time it's going to be a polynomial q of x, and you're going to get a remainder polynomial r of x. So what that means is that you're really saying that the f of x, which we're going to call the dividend, equals the divisor h of x times the quotient q of x plus your remainder r of x. All right. Now that remainder could be 0 if it divides cleanly into the polynomial, or it has to have a degree less than the degree of the divisor, and we'll see that. So if this sounds a little intimidating, don't let it be, because you've done this type of thing with dividing numbers, because remember, numbers are just constants. They're actually 0 degree polynomials, so you've actually divided polynomials. You were only just dividing the simplest of polynomials. So let's take a look. So if we wanted to divide 3,467 by 7, all right, so how would that be done? Well, if you remember, you'd write 7 into 3, 4, 6, 7. Okay, and you'd be asking yourself first, Can 7 go into 3? All right. Well, no. So then we go further. So can 7 go into 34? Yes. And how many times? Well, you can go in 4 times without going over. So I put a 4 there, and then we multiply these, and we get 28, which we put right underneath, and we subtract, and 34 minus 28 is 6. We write that there. So that's our first step. Then we're basically going to repeat again, but 7 can't go into 6, and it shouldn't be able to, because otherwise we would have had a bigger number that we went into the previous one. So we bring down that 6 to say now we're going to look at putting 7 into 66. All right, 7 goes into 66 9 times without going over, and you get 63, which we're going to subtract. And then you get 3. 7 can't go into 3, it shouldn't. So we bring down 7. Now 7 into 37. Well, that goes in 5 times without going over. You get 35. Subtract, and you get 2. All right. And then at this point, 7 shouldn't be able to go into 2, and there's no more. So that's actually your remainder. So you have a remainder of 2. So that's the division we're talking about. So in terms of terminology here, this 7 here was the divisor going into the 3, 4, 6, 7 is the dividend. And we got this 495 as our quotient with 2 as our remainder. Okay, but let's see what we really mean by what we've just done. So we've shown that 3,467 could be expressed as 7, the divisor, times 495, the quotient, plus the remainder of 2. And this is the kind of format we're going to want to look at because this is kind of like trying to factor 3,467. Now we found it didn't factor nicely with these numbers because there was a remainder. So if it had factored into the product of 2 other numbers, then we would have had a remainder of 0 here, and that's the kind of thinking that we're going to want to do moving forward. So even though, yes, you could say that 3, 4, 6, 7 divided by 7 is 495 plus 2 over 7. That is another way of writing this. In fact, that's just taking everything from here and dividing it by 7. And so this is one nice way to look at it in some contexts. Here, we're going to look at it like this.